Hello and welcome to topic 38 of OCR A Level Chemistry. This is the last topic and we've saved the best to last. This is all about NMR spectroscopy. NMR stands for nuclear magnetic resonance, and you don't need to know anything about how a nuclear magnetic resonance spectrum is formed. I'm going to tell you a little bit just so you've got some basics. A small sample of whatever it is that you're testing is put in a very strong magnetic field, and that causes atoms to line up with that strong magnetic field. Now you can shine in a small amount of an electromagnetic radiation to make them flip their position. You don't have to understand why or how, but that small amount of radiation can be detected, and so you can detect what type of environment each of the atoms is in based upon how much energy it takes to make it flip. And that's essentially what we plot on the graph. It's the amount of energy it takes to make it flip, but most importantly, that amount of energy is very indicative of the position of that atom in a molecule. So different atoms in different environments in a molecule absorb different frequencies or energies of electromagnetic radiation, and that tells you about where that atom is in a molecule, so how close it is to electron density or anything. And for this topic, you're going to need the data sheet more than ever, because on the data sheet it tells you where carbon atoms absorb, and it also tells you where hydrogen atoms absorb. And carbon-13 and hydrogen, NMR, those are the ones we're going to talk about during this topic. Now in the exam you'll get the data sheet, and this part I don't think it's very clear, but the top tells you about the carbon absorbances, and then the bottom tells you about the hydrogen absorbances. And so we're going to talk about carbon-13 NMR and proton NMR, or hydrogen NMR. But before we do that, I'm just going to go a little bit into what I meant by environments. So in this molecule I've got 9 carbon atoms. There are 6 in this benzene ring, 1 there, and then 2 in the ethyl group. But when we're talking about carbon environments, or how many carbon environments there are, we're looking for carbons which are different from every other carbon. I want to count up how many different types of carbon there are. And to do that, the best way I can think of doing it is to look at what they're bonded to. So if they're bonded to the same thing, if 2 carbons are bonded to the same atoms, or the same types of atoms in the same places, then they're in the same environment. I'm going to look for any carbons which are in the same position as each other. And normally, that's to do with symmetry. So we have this carbon on the end. I'm going to start there. It's obviously different to other ones because I haven't started counting yet. That's the first one. So there's going to be at least 1 carbon environment. That's the first one. Now I look at the next carbon. Is that carbon different to the first one? Well, yes. This is a CH3 and this is a CH2 group. This one's also next to an oxygen. So it's clearly in a different position. Next up we have this carbon atom. Now that is different from both of these two because it's double bonded to an oxygen and single bonded to an oxygen as well. So that's in a different environment to this one and to that one. So that's the third environment. Next carbon on is this one. That's part of a benzene ring, so clearly different to any of the ones so far. And then we look at this one. That one's different to any of the ones we've seen so far as well. It's in a benzene ring, but this one was also bonded to a carbon of a carbon, whereas this one isn't, so that's in a different position. The next one along, now this looks very similar to that one, but if you look at the bonds it's making, then this one, carbon 5 as I've called it, is 1 step away from carbon 4, whereas this one is 2 bonds away, so that's different. Next up is this one, which is opposite 4. That's different from 6 and 5 because it's opposite 4, so it's 3 bonds away. And this is where it gets interesting, because the next 2 are actually not different. If you look at this one, then that is in the same position as carbon number 6. It's 2 away from 4, and it's 1 away from 7. It's in the same position as 6 is. So it is just another carbon in the environment that I've called 6. And this carbon here is 1 step away from 4, 1 step away from 6. It's 2 away from 3, the same as 5 is. It's in every way bonded the same as carbon 5, and so it's in the same environment as carbon 5. So the number of different carbon environments, 7. So we've got 9 carbon atoms, but they're in 7 different environments. And now let's do hydrogens. A lot of the time, hydrogens is very similar to carbons. So if the carbon that a hydrogen is bonded to is in the same environment as another carbon, then they're going to be the same. This one is carbon number 1. It's got hydrogens bonded to it, and so those hydrogens are in the environment. I'm going to call it 1 because it's on carbon 1. If you look at this one, then it's got 2 hydrogens on it. Both of those 2 hydrogens are in the same environment because they're bonded to the same carbon, and because that carbon is different to this carbon, that must mean that the hydrogens bonded to it are different to the hydrogens bonded to 1. Now, number 3 and 4 don't have any hydrogens attached to them, so I'm just going to ignore those and move to 5. Carbon 5 has 1 hydrogen attached to it, and so that's in a different environment to either of these. These are alkyl, this is on a benzene ring, so that's different. Carbon 6 is different to carbon 5, so the hydrogen attached to carbon 6 is different from the hydrogen attached to carbon 5, so that's different to 3. Same for 7, and then same as before, carbon 6 here is the same as carbon 6 here, so the hydrogen attached to it must be in the same environment as well. And that's the same with these 2 carbons and the 2 hydrogens attached to them. That means that the number of hydrogen environments is 5. There's 10 different hydrogens, but there are only 5 different environments. Okay, so why did I do that? What was the point of counting the number of environments? Now, if you think back to what I said about NMR, NMR measures basically the number of environments. It doesn't tell you a number. What it does is give you peaks where they absorb. But the carbon one will have 7 peaks, and the hydrogen one will have 5 peaks. So the carbon NMR is going to have 7 different peaks. You have a peak for that carbon, for the second carbon, for the third carbon, the fourth. The peak for the carbons which I've labelled 5 is going to be twice the size as the peak for the carbons I've labelled 1, 2, 3 and 4. And that's the same for 6, it's going to be twice the size as 4, 3, 2 and 1, and the same size as peak 5. And then the peak for 7 is going to be the same size as 1, 2, 3 and 4. So that peak size is determined by how many carbons are in that environment. So if there's twice as many carbons, you've got twice the size of the peak. And if you look at the data sheet, you can work out where those carbons will be. And my data sheet says that carbons which are bonded just to other carbons on a single bond, that could be anywhere between 0 and 50. And so carbon number 1 is just bonded singly to another carbon. That could show up anywhere between 0 and 50 parts per million, ppm. Any carbon which is bonded to an oxygen will show up between 50 and 90. And so carbon number 2 will be somewhere between 50 and 90, there will be a peak. Carbon number 3, which is a carbon of a carbonyl bond, is all the way up between 160 and 220. So you get a peak between those, which is size 1. And then 4, 5, 6 and 7 are all part of the benzene ring. And on the data sheet, the benzene ring is between 110 and 160 parts per million. So you'll have 4 peaks, 2 of them small and 2 of them big, all between 110 and 160 parts per million. And so it's possible, if they give you a blank graph, to ask you to draw what you think this carbon NMR might look like. You see, you'd have 1 peak between 0 and 50 for that carbon, so I'll just put that there. Moving along, this carbon bonded to an oxygen was somewhere between 50 and 90, so you'd have a peak the same size as this one, but between 50 and 90. Then the next carbon, carbon 3, would have a peak somewhere between 160 and 220, and it should be the same size as the other 2 peaks. And then I said between 110 and 160, you'd have 4 peaks due to 4, 5, 6, and 7. And so they could fall anywhere in that range. And so I've just drawn 4 peaks there, 2 of them twice the size of the other 2. So they'd be due to 5 and 6. And it's equally possible that you could go the other way around. You could get this NMR and asked how many different carbon environments there are. So you just count the peaks, 1, 2, 3, 4, 5, 6, 7. And you could also be asked how many carbons there are, I suppose. So there's 7 different environments. 2 of them have clearly got 2 carbons in, so that's 9 different carbons. Now you wouldn't be able to distinguish that from 18 carbons, because it could equally be 2, 2, 2, 4, 2, 4, 2, which would be twice as many carbons. And so all you can really work out is the ratio of the carbons in those environments. But if you were given an NMR and also a mass spec, then the mass spec you could look at the molecular ion, and from that, how many different carbon environments there were, and how many carbons there were in total. And you can do a very similar thing with hydrogen. Hydrogen NMR, you can do low resolution hydrogen NMR, in which case you get something that's actually quite similar to this, but the numbers are different. But if you do high resolution proton NMR, so the same but with bigger magnets and more accurate techniques, then you can get much more information. And so it's much more useful for working out the structure of a molecule, and I'm going to spend a little bit of time on that now. And I'm going to use the same molecule as I used before, but this time I'm going to put on the hydrogens so we can see what we're working with. Okay, so here are 10 hydrogens, and we've already discussed which ones are in which environment. We've got 5 environments. These first 3 are in one environment, these 2 are in a different environment, these 2 in a third environment, 4th environment for those 2, and then the one on the end, that's the 5th environment. And so we should expect 5 different peaks. But there's more information you can get, and it's more complicated than that, so that's what I'm going to go through now. The first thing I'm going to do is just look at where they are and the data sheet to work out where those peaks should occur on the NMR spectrum. So in the same way as I did with the carbons, this one is an alkyl group, so a hydrogen attached to a carbon in an alkyl group will be in a specific place on the NMR. The same for a hydrogen attached to a carbon next to an oxygen, that's going to be in a different place because the carbon's next to an oxygen. Also, if it was next to a carbonyl group, that would be different. And if it was on a benzene ring, that's going to be different again. So I'm just going to look at the data sheet and find out where each of these hydrogens shows up on the data sheet. Okay, so to get these shifts, these chemical shifts, all I did was look at the data sheet to see where a H bonded to a carbon in a carbonyl would be. Now on the data sheet, that's written as HCr, so that's H on a C, which is bonded to an R. The next one would say HCO, so H on a C bonded to an O. And then the only other ones we've got are these 5, which are all H on a benzene ring. And that's got a specific place on the data sheet where it shows up. And so when we look at the NMR, what we're expecting is 5 peaks in those 5 places. And the next bit is very similar to the carbon NMR, where if the peak is twice the size, then that means there's twice as many carbons. And this one's very similar. What they do is just measure the size of the peaks and then make a ratio of those. So what you'd end up with is this would be a peak size of 3, this would be a peak size of 2, these would make a peak size of 2, these would make a peak size of 2, and then the last one would just be a peak size of 1. And so this one would be the biggest peak, and that one would be the smallest peak. And a lot of the time in the exam, what they'll do is write next to the peak, in bold, a number, and that number is the number of hydrogens in that environment. So instead of having you measure the size, actually what they'll do is write next to the peak the size of that peak. So I'm going to call that the integral, because you measure the size of a peak by integrating under the curve to find the area of that peak. And so the peak between 0.5 and 1.9 would be an integral of 3, integral of 2, integral of 2, integral of 2, integral of 1. And these integrals should add up to the number of hydrogens you've got. So 3 and 2 and 2 and 2 and 1 all add up to 10, which is the same as the number of hydrogens that I've got. And that makes sense because the integral of 3 means that there's 3 hydrogens, and the integral of 2 means there's 2. So if I add up all of those numbers, I should get the number of hydrogens that there is in the whole molecule. And so what was all this extra information? There's really just one bit, and that is when you've got hydrogens which are attached to a carbon adjacent to a carbon that has hydrogens on it, they interfere with each other. So, for instance, these hydrogens, the hydrogens which I've labelled 1, and these hydrogens which I've labelled 2, they would interfere with the peak of the other one. And so the peak for these 3 will be split by these 2, and the peak for these 2 will be split by these 3. It only has an effect if the carbons are directly adjacent to each other, so directly bonded to each other. And so, for example, this number 5 would have no effect on number 3, only on number 4, because the carbons are directly bonded to each other. And so, whereas before we saw individual peaks, I accidentally said it earlier, but it splits that peak. So instead of having 1, you've got 2 or 3 or 4 sub-peaks. And the number of sub-peaks is determined by the number of hydrogens which are splitting it. So, for instance, this is 3 hydrogens, they make a peak. And that peak is split by each of those hydrogens. If it was 1 hydrogen, it'd be split into 2. But it's 2 hydrogens, and that is split into 3. And it's called the n+1 rule. However many hydrogens there are, you get that many plus 1 sub-peaks. So instead of having 1 peak, you'd have 3 peaks. And that 3 peaks is called a triplet. So I've written up there that H2, so these, split H1 into a triplet. And then also, H1 are going to split H2 into a quartet. So remember, it's 1 more than the number of hydrogens which are splitting them. And so there's 3 hydrogens, so H2 is going to be split into a quartet because it's been split 3 times by these 3 hydrogens. And I'll draw out what I mean by a triplet and a quartet in a minute. If it's just 1 sub-peak, then just 1 peak, it's a singlet. And if it's 2 sub-peaks, it's a doublet. Any more than 4, and you just call it a multiplet. You can do pentet or hexet or heptet, but normally if it's more than 4, you just say multiplet. So many sub-peaks. But before I do that, I'm just going to go over the other ones. So H3 is going to be split by H4 into a doublet, because it's 1 hydrogen on the adjacent carbon, which makes it a doublet. And then H4 is going to be split into a doublet by H3, and then another doublet by H5. And so we don't have to deal with that. It's called a doublet of doublets, but we're just going to call that a mess or a multiplet. And the reason why it's not split into a triplet, you might be thinking, is next to two hydrogens, so it'd be split into a triplet, and that would make sense. But because H3 and H5 are different, they split differently, and so instead of splitting and then splitting again to make a triplet, it split it and then split it again, but in a different way to the first split, which makes just two different splits, and that's called a doublet of doublets, so two doublets. The last one is H5. Now H5 is being split twice by H4, and so that is going to become a triplet, because it's two splits, both from the same type of hydrogen. Okay, now that seems like a lot, but all of this is the same as for carbon. You've got the specific shift, depending on what that environment is, and you've got the integral, which tells you how many things are in that environment. Now this bit, the splitting, may seem complicated, but it's actually very useful, because it tells you not only what the environment is, which you get from this, but what's in the environment next to it. And so it helps you to piece together the molecule. So let's now draw this NMR, and I'll show you what I mean by singlet, doublet, triplet, quartet, and multiplet. Okay, so let's start with the top one. We're going to have an integral of 3 peak, 0.5 to 1.9, so somewhere in that range, and it's going to be a triplet. And a triplet has a very specific shape. It's got 2 on the outside, which are half the size of the one in the middle. Okay, so this is what I mean by a triplet. It's 3 small peaks all grouped together. The 2 on the outside are half the size of the one in the middle. So that peak is going to have a size of 3, and it is due to these 3 hydrogens, which are in an alkyl group, so that's why they're between 0.5 and 1.9, and they are next to 2 hydrogens, which is why it's split into a triplet. Next peak I'm going to do is this one, which is these 2 hydrogens. So it's going to have an integral of 2, it's going to be somewhere between 3 and 4.3, and it's going to be split into a quartet. Now in a quartet, the 2 on the outside are 3 times smaller than the 2 in the middle. And so it looks something like this. Now I'm going to say this now because it comes up all the time. If you have a quartet with an integral of 2 and a triplet with an integral of 3, almost certainly what you've got is an ethyl group. So it's 3 being split by 2 and 2 being split by 3. And that leads to this very specific shape. Now often what you'll see is the 2 hydrogens, the quartet, being slightly further up because they're next to an oxygen. It's just the way that the questions tend to roll. Now what we've got left is all of these 3, which are going to be in the same position. We're going to have 2 peaks with integral 2, 1 with integral 1. One of them is going to be a doublet, one's going to be a triplet, one's going to be a multiplet. And actually what you get is all of these overlapping with each other. So you don't get 3 nice peaks. What you'll almost always end up with is just a mess of 1 peak over another peak over another peak. So if you imagine me drawing a doublet and then drawing a multiplet over the top and then a triplet over the top of that, that's what it's going to look like. And it's going to be somewhere between 6.2 and 8. And so you can see this just looks like a mess, and that's because I just drew a mess. I didn't try and draw these 3 things over the top of each other, because you don't need to be able to kind of decipher that. What you need to go is this, and it happens a lot as well. Anytime there's a benzene ring, this tends to happen. You have an integral of 5, because it's just the combination of all of these 3, and they're all around 7, because that's where benzene goes. And so what this means is 5 hydrogens on a benzene ring. And what that tells you is that there's 1 group on that benzene ring. So there's 5 hydrogens, and then 1 other thing bonded to that benzene ring. Right, so I'm going to quickly go over a little bit of like housekeeping before I go on to how do you go back from this to a chemical. And there's a couple of things that are on the specification you need to know. The first one is that they use a compound called tetramethylsilane, or TMS, to determine where 0 is. So sometimes you'll see a little peak at 0. That doesn't mean any hydrogens are there. That's the peak due to tetramethylsilane, or TMS. And that is used as a standard to make sure all of the NMRs start at the same place and so shift to the same places. You'll notice on the data sheet that none of the actual groups go far as 0, and that's because none of them go as far as 0, so don't try and label that peak as anything apart from TMS. The next thing, if you look at the data sheet, you'll see that OHs, so the hydrogens of alcohols, and NHs, they show up wherever they please. So it can be anywhere between 1 and 12. So if you see a random peak somewhere you can't assign, they're always singlets because they're not bonded to any carbons. That could be an OH or it could be an NH. That's only for proton NMR. And the reason that they can show up anywhere is because they interact with the solvent. And so that piece of information can also be useful for removing them. So if you don't know if it's an OH or an NH, you can change the solvent so that the solvent interacts with that hydrogen in a way that doesn't allow it to show up on the NMR spectrum, and then you'll see that peak disappear, and whatever peak that disappears that is the peak which was due to an OH or an NH. And the specific solvents you use are solvents which are deuterated water, so heavy water, D2O. And what that means is, instead of hydrogen in the solvent, they've got deuterium. Now, deuterium doesn't show up on this, it's always H1, so protein, hydrogens with one proton and no neutrons. Deuterium is one proton, one neutron, and it doesn't show up on an NMR spectrum. And so when you put the deuterated solvent in with something which has got an OH or an NH peak wandering around, then the deuteriums will swap over and over with that NH or the OH, and it never shows up on the spectrum. You need to use a deuterated solvent any time you run an NMR. Just imagine you use like propanone as your solvent. Propanone's got hydrogen in it, and there's always more solvent than there is the chemical, the sample that you're measuring. And so what you'll end up with is all of these peaks, but then an absolutely massive one due to the hydrogen that's in the solvent. And so it needs to be a deuterated solvent because, as I said, deuterium doesn't show up on an NMR. Now, the last thing I'm going to do is show you how you would get back from a spectrum to a molecule. And also, just as importantly, how I would answer the question to make sure I got all the marks. I'm going to use the same spectrum to see if this spectrum is actually due to only one type of chemical or if there could be more than one chemical which comes up with this spectrum. So what I'm going to do is analyse the spectrum. I'm going to start off with this peak, and it's got a triplet, that means it's next to two hydrogens. It's between 0 and 1, that's about 0.6, and it's got an integral of 3. So that tells me loads of information. So let's just write down that information. I'm going to call this peak 1. So if you know what you're doing, you can do loads with that one little peak. Now it's at 0.6 ppm. If you look on the data sheet, there's only one thing which occurs there, and it is CHR. So we know that it's a hydrogen in an alkyl group. Integral 3, that means that it's probably going to be a CH3. It's a triplet, which means that that CH3 is next to a CH2. So that's already loads of information. If we continue doing that, we'll end up with all the information we need. So the next peak, we'll call that peak 2. Okay, so I've done exactly the same with the next one. It's at 4.0 ppm, which means that it's either a hydrogen on a carbon bonded to an oxygen, or a hydrogen on a carbon bonded to a bromine, or a hydrogen on a carbon bonded to a chlorine. Now, you normally get other information, such as molecular formula or a percentage by mass, which you can work empirical formula out from. And I'm going to assume that I've got that information and know there's no bromine or chlorine. So I know that this is a CH bonded to an O, neither of those. It's got an integral of 2, which means that it's a CH2 group, and quartet means it's next to a CH3. Now, if you're paying attention, you'll see that this is a CH3 next to a CH2. This one is a CH2 next to a CH3, and so those two are kind of paired up. It's a CH2, CH3 group. And we also know that that carbon of the CH2 is next to an oxygen. And so the next thing after that carbon is an oxygen. And so we're getting there. Let's continue and do the next one. I'm going to call this peak 3. So this next peak is at 7.4 ppm. That means if you look at the data sheet, there's got to be a benzene ring, or hydrogens on a benzene ring. It's got an integral of 5, which means that there's 5 hydrogens on that benzene ring, leaving one group, and it is a multipair. Now, that just means that it's 5 hydrogens on a benzene ring. I'm not going to go into it any more than that. And so at this point, without any further information, like a carbon NMR, or an infrared spectrum, or a mass spectrum, or empirical formula, or molecular formula, we could draw a couple of different things. What we really need is a little bit of extra information, just like a molecular formula, so that I know that I've got all of the carbons that I need. Because any carbon which doesn't have a hydrogen on it isn't going to show up on this hydrogen NMR. And so that's why this carbon R group, at this point we don't know that's there, because we need some extra information. You could get, for instance, an infrared, which has got an absorbance at 1700 per centimetre, which tells you there's a carbon R group. And so we haven't got a carbon R group yet. We don't even know about the existence of a carbon R group, because it's not next to any of our hydrogens. And so we don't know it's there. But with an infrared, we would know it's there. Sometimes it says in the question that it's an ester, in which case we know we're looking for a carbon R group. If we had a molecular formula, we'd know we had one too few carbons. The minute I only got 6, 7, 8 carbons. If I knew I had 9 carbons and 2 oxygens, then the next logical step is to put a carbon and an oxygen in as a carbon R group. But let's say that this is the only information we've got. We could draw this structure, and this molecule would give a very similar NMR spectrum. Because it's a hydrogen NMR, and so the carbon R is just not going to show up on it. Now let's assume we got told that it was an ester. Which way round you put the ester? We know we've got this C6H5 group, we know we've got this CH2CH3 group, but we also know that the carbon is bonded to an oxygen because of this chemical shift. And so we know we need to put the ethyl group on the oxygen, the ester, and this phenyl group on the carbon of the ester. And so that's what leaves us with this as our answer. And so when they give you extra information, use that information. If they give you percentage mass of elements, use that. As GCSE, just take those percentage masses and work out an empirical formula. Use the mass spectrum or the molar mass that they give you as well to go along with that empirical formula to work out the molecular formula. And you've got so much more to go on. You know if you're missing out atoms. You know if you're missing out hydrogens. You know if these numbers, 5, 2 and 3, don't add up to the number of hydrogens you've got, then something's gone wrong somewhere. And when it comes to answering the question about the NMR, be very, very logical. So what I've done here is included every piece of information that I could possibly want and made links between them. So I said the chemical shift, I said what that means on the data sheet, so what environment is it in. I said the integral and what that means about my hydrogens. I said the splitting pattern and what that means about the adjacent carbon. I've done that for all of them that I can do. So the multiplet makes it difficult, it just basically means you haven't got enough information. And then take the groups that you know you've got and then try and arrange them in a way and draw out a structure. If you draw out the wrong structure, like if you have the ester the wrong way round, then you only lose 1 mark. And normally you get 4 marks for a structure like this. And so drawing it out is always worthwhile having a shot and checking that you've got the same molecular formula that you got from the empirical formula and the mass spectrum. Always have a go at drawing something given the information that you've got. And use the data sheet and those chemical shifts that are on the data sheet to try and work out, even if you can't work it out completely, you can work out that if it's got stuff at 7, then it's going to have a benzene ring. And that tells you a lot of what you've got. Benzene ring, and there's 5 hydrogens on that benzene ring. You can just start to piece together the molecule. And that is it for this topic on spectroscopy, and for the A2, and for the entire A level of OCR chemistry. Thank you very much for watching. Good luck.